Hello and welcome to Random Topics with Jack, the podcast where we explore the intriguing and sometimes controversial topics that shape our understanding of the world. In our last episode, we took a fascinating trip to the history of linguistics. We explored the fundamental building blocks of language, from its smallest sounds and structures to how we process it all in our brains, and even delved into the origins of major language families like Indo-European. And it was quite the linguistic journey, and I hope you found it as enlightening as I did. Today, however, we are shifting gears entirely. We're leaving the nuanced world of grammar and syntax and venturing into the very building blocks of our universe. We're diving into the captivating world of the periodic table. We'll be exploring its origins, the brilliant minds behind its creation, the human dramas and rivalries that shaped its development, and how this iconic chart became the cornerstone of modern science. Get ready to have your mind opened to the incredible order and predictive power of the elements. Let's get started. Before the periodic table as we know it, elements were like a collection of unique but uncatalogued treasures. Scientists were busy isolating and identifying them, but there wasn't a clear system to organise this growing list. Think of it like having a massive pile of unique Pokemon cards without any idea of their types or rarities. By the mid-1800s, chemists had identified about 60 elements, but they were essentially working with the chemical soup of disconnected facts. They knew that sodium exploded when it touched water, that gold didn't tarnish, and that chlorine was a deadly gas, but there seemed to be no rhyme or reason connecting these properties. It was frustrating, chaotic, and frankly a bit overwhelming for anyone trying to make sense of chemistry. Then came the pioneers, and their stories are absolutely fascinating. Johann Döbereiner, working in Germany back in 1829, was actually investigating the properties of newly discovered elements when he stumbled upon something remarkable. Picture this. He's in his laboratory, methodically testing the properties of lithium, sodium, and potassium. These three metals all react violently with water. They all form similar compounds, and here's the kicker. When he looked at their atomic weights, sodium's weight was almost exactly the average of lithium and potassium's weights. But Döbereiner wasn't content with just one example. He found the same pattern with chlorine, bromine, and iodine, three halogens that formed similar compounds, but had this same mathematical relationship in their atomic weights. He called these groupings triads, and while he couldn't explain why this pattern existed, he uncovered the first hint that the elements weren't as random as they seemed. Around the same time, or rather a bit later in 1862, French geologist Alexandre-Émile Bigoya de Chancourtois was thinking literally outside the box, or rather around the cylinder. This man had a wild imagination. He took all the known elements and arranged them in a spiral around a cylinder based on their atomic weights. He called this contraption the telluric helix, telluric meaning of the earth. Picture a barber pole, but instead of red and white stripes, it's covered in element names spiralling around. The genius of this design was that when you looked at the cylinder from the side, elements with similar properties lined up vertically. It was brilliant, three-dimensional thinking that showed periodicity in a completely new way. Unfortunately, the scientific community largely ignored it, partly because Chancourtois published it in a geology journal rather than a chemistry journal, and partly because people just weren't ready for such a radical visualization. And then in 1864, John Newlands, with his musical approach to chemistry, this English chemist noticed something that seemed almost too poetic to be scientific. When elements were arranged by increasing atomic weight, every eighth element seemed to have similar properties, much like musical octaves where every eighth note sounds similar. He called this the law of octaves. Now, here's where the story gets a bit sad and infuriating. When Newlands presented his idea to the Chemical Society of London, the reception was brutal. One particularly snarky member asked if he'd tried arranging the elements alphabetically instead, essentially treating his serious scientific work like a joke. The president of the society refused to publish his paper, calling it too theoretical and lacking an experimental foundation. The irony? Newlands was absolutely right. His pattern held true for the lighter elements, and his insight about periodicity was fundamental to what would later become the modern periodic table. But sometimes being ahead of your time means being dismissed by your contemporaries. Despite the initial resistance and ridicule, these early attempts were crucial steps, laying the groundwork for the revolutionary discoveries that were yet to come. The landscape of chemistry was irrevocably transformed by the sheer brilliance of Dmitri Mendeleev. But before we dive into his scientific achievement, let me paint a picture of the man himself and the dramatic circumstances surrounding his discovery. It was 1869, and Mendeleev was a 35-year-old professor at St. Petersburg University, struggling with a problem that was consuming him entirely. He was trying to write a chemistry textbook and couldn't figure out how to organise the elements in a logical way. For days and nights he obsessed over this puzzle, writing element names and properties on individual cards and shuffling them like a mad gambler trying to find the winning combination. Legend has it, and I say legend because Mendeleev told this story in his later years, that after 3 days of sleepless work, he finally collapsed at his desk, utterly exhausted. And in his dream, he saw a complete table where every element fell into place. When he woke up, he frantically wrote down what he remembered from the dream. Supposedly, only one correction was needed to make it perfect. Now, whether or not the dream story is true, what we know for certain is that Mendeleev's approach was revolutionary. He wasn't just listing elements, he was revealing an underlying cosmic rhythm. His genius lay in his dual approach. He meticulously arranged the known elements by increasing atomic weight, but his true stroke of brilliance was prioritising the groups of elements by their recurring chemical properties. And here's what made Mendeleev truly extraordinary. When the atomic weight order conflicted with chemical similarity, he trusted chemistry over mathematics. Now this was audacious. Imagine telling your mathematics professor that you're going to ignore the numbers because your gut feeling about patterns tells you something different. But the most astonishing aspect of Mendeleev's work was his extraordinary foresight. He boldly left gaps in this table, recognising that undiscovered elements must exist to fill these spaces. More than just leaving gaps, he predicted the properties of these missing elements with remarkable precision. Take his prediction for what he called eka-aluminium, literally meaning beyond aluminium. In 1871, Mendeleev predicted this element would have the atomic weight of around 68, would be a metal that could be isolated by electrolysis, and would have a density of about 6 grams per cubic centimetre. Would form an oxide with the formula M2O3, and would form salts with acids. 4 years later, Paul-Émile Lecoq de Bois-Baudran discovered gallium in France, and when the properties were measured, they were almost eerily accurate to Mendeleev's predictions. Atomic weight, 69.7. Density, 5.94. And it formed exactly the compounds Mendeleev had predicted. It was like Mendeleev had sketched the silhouette of a yet unseen creature based on the footprints it left behind. The scientific world was absolutely captivated. When elements like gallium, scandium and germanium were subsequently discovered, their properties aligning almost perfectly with Mendeleev's predictions, this table wasn't just accepted, it was hailed as a monumental achievement. This validation cemented the periodic table's importance and Mendeleev's place as the architect of chemical order. But what was truly happening in Mendeleev's life during this time? This wasn't just academic curiosity. His career and reputation were on the line. Russian science was trying to establish itself on the world stage, and Mendeleev desperately wanted to contribute something significant to human knowledge. The pressure was immense, and his obsession with organising the elements was as much about personal validation as it was about scientific progress. Now here's where this story gets really juicy, because science is never just about pure discovery. It's about people, egos, and national pride. While Mendeleev was working on his table in Russia, a German chemist named Lothar Meyer was independently developing something remarkably similar. In fact, Meyer had been working on his own periodic arrangement since 1864, but he was cautious, methodical, and unfortunately for his place in history, slow to publish. Meyer's approach was different, but equally valid. He created graphs showing how atomic volume varied with atomic weight, revealing the same periodic pattern that Mendeleev had organised into his table. When Meyer finally published his complete work in 1870, just 1 year after Mendeleev, he found himself in the awkward position of appearing to have copied the Russians' work. The rivalry between Mendeleev and Meyer became a source of national tension. German scientists supported Meyer, Russian scientists backed Mendeleev, and the international chemistry community was forced to choose sides. Ultimately, history sided with Mendeleev, primarily because his table made specific predictions about undiscovered elements, while Meyer's was more descriptive of known patterns. But here's the tragic irony of scientific recognition. Despite creating what is arguably one of the most important organizational tools of all of science, Dmitri Mendeleev never won a Nobel Prize. When he was nominated in 1906, he lost by a single vote. The official reason was that his discovery was too old. The Nobel Committee preferred to reward recent discoveries. Mendeleev died the following year, never having received his ultimate scientific recognition. And the politics didn't end there. Different countries began claiming credit for various aspects of periodic law discovery. The French promoted Chancourtois' earlier work, the Germans championed Meyer, and the English pointed to Newlands' octaves. It became a matter of national scientific pride, with each country wanting to claim a piece of this fundamental discovery. While Mendeleev's table was revolutionary, science never stands still. The next major leap came with the discovery of the atomic number, and this story involves one of the most tragic figures in scientific history. Henry Moseley was a brilliant young English physicist, only 26 years old when he made his groundbreaking discovery in 1913. Working at the University of Manchester, Moseley was experimenting with X-ray spectroscopy, a cutting-edge technique that involved firing X-rays at different elements and analysing the patterns they produced. What Moseley discovered was revolutionary. Each element produced a unique X-ray signature that corresponded not to its atomic weight, but to what he called its atomic number, the number of protons in the nucleus. And this was a more fundamental property than atomic weight. It resolved all the anomalies that had puzzled chemists. Remember how Mendeleev had to place tellurium atomic weight to 127.6 before iodine, atomic weight 126.9, to keep elements with similar properties together? It seemed to violate the principle of organising them by atomic weight, but using Moseley's atomic number, iodine with 53 protons correctly comes after tellurium with 52 protons. The same solution applied to other problematic pairs like argon, potassium, and cobalt and nickel. Moseley's work was so precise, he could predict exactly which atomic numbers were missing from the periodic table. He identified gaps at numbers 43, 61, 72, and 75, predicting that 4 elements remained to be discovered. And he was absolutely correct on all counts. But here's the heartbreaking part of the story. In 1915, just 2 years after this monumental discovery, Henry Moseley was killed in action at the Battle of Gallipoli during World War I. He was only 27 years old. Scientists around the world mourn not just the loss of a brilliant mind, but the untold discoveries that died with him. Many historians believe that if Moseley had survived, he would have certainly won a Nobel Prize and likely made additional groundbreaking discoveries that could have accelerated scientific progress by decades. Moseley's death was such a shock to the scientific community that it led to a policy change. During World War II, scientists involved in critical research were exempt from combat duty. The loss of Henry Moseley taught the world that brilliant scientific minds are too valuable to lose in warfare. And all of this leads to the modern periodic table that we recognise today, built on the foundation of Moseley's atomic number principle. It's arranged by increasing atomic number, with elements organised into horizontal rows called periods and vertical columns called groups. These groups often share similar chemical properties due to their electron configurations, which dictate how atoms interact. The modern table also reveals the elegant structure of atoms themselves. We see elements categorized into blocks S, P, D, and F, based on the orbitals of their outermost electrons. And this isn't just organizational, it's predictive. The position of the elements tell us how it will behave chemically, what kinds of bonds it will form, and how it will interact with other elements. But the story doesn't end with Moseley's discovery. The table continues to evolve as we push the boundaries of what's possible. Today, scientists are still expanding on the periodic table, but they're working in a realm that would have seemed like science fiction to Mendeleev and Moseley. We're creating elements that exist for mere milliseconds before decaying, elements so unstable that only a few atoms have ever been produced. The challenge of superheavy elements is mind-boggling. Elements beyond number 118, oganesson, the heaviest element currently on the table, lasts only fractions of a second. Creating them requires smashing lighter atoms together in particle accelerators with such precision and energy that success rates are measured in individual atoms per week of continuous bombardment. So why do scientists bother with elements that vanish almost instantly? Well, because theory predicts something called the island of stability, a region around element 114 to 126 where superheavy elements might be relatively stable, possibly lasting minutes, hours, or even years. Imagine elements with properties we've never seen, potentially useful for technology we can't yet envision. The naming of new elements has become its own source of controversy. When elements 113, 115, 117, and 118 were confirmed in the 1980s, there were disputes over the naming rights between Japanese, Russian, and American research teams. The International Union of Pure and Applied Chemistry had to step in to mediate, leading to names like Nihonium, honouring Japan, Moscovium, honouring Moscow, and Oganesson, honouring Russian physicist Yuri Oganessian. But here's a mind-bending question. Is there a limit to how many elements can exist? Theoretical physicists suggest that around element 137, the mathematics of atoms breaks down. At that point, electrons would need to travel faster than light to maintain stable orbits, which violates the laws of physics as we understand them. Element 119 and 120 are currently being pursued by laboratories around the world, but each new element becomes exponentially more difficult to create and detect. But let's zoom out from these earthly laboratories and consider the periodic table from a cosmic perspective, because the story of elements is really the story of the universe itself. Every element heavier than hydrogen tells the story of stellar death and cosmic violence. When Carl Sagan famously said, "We are made of star stuff," he was referring to the process of stellar nucleosynthesis, the cosmic factories where elements are forged. In the cores of stars, hydrogen fuses to create helium. Helium fuses to create carbon and oxygen, and this process continues up through iron. But here's where it gets dramatic. Creating elements heavier than iron requires more energy than it produces. This can only happen during the catastrophic explosions we call supernova, when dying stars release more energy in seconds than our sun will produce in its entire 10 billion year lifetime. This cosmic perspective explains why the universe is dominated by hydrogen and helium. They were created in the Big Bang itself. Everything else, from the carbon in our bodies to the gold in our jewellery, was forged in the nuclear furnaces of stars or in the violent collisions between neutron stars. When you look at the periodic table, you're looking at a timeline of cosmic evolution. The abundance of elements in the universe follows predictable patterns based on this stellar nucleosynthesis. Hydrogen makes up about 75% of all normal matter, helium about 25%, and everything else, every other element in the periodic table, comprises less than 2% of the universe. This is why gold is precious, not just economically, but cosmologically, because it's incredibly rare and it requires a violent cosmic event to create. Even more remarkably, we can detect what elements exist in different stars by analysing their light. When starlight passes through a prism or spectrometer, it creates a unique fingerprint of absorption lines that correspond to different elements. This technique, called spectroscopy, allows us to know the chemical composition of stars thousands of light years away with remarkable precision. The periodic table isn't just useful on Earth, it's our key to understanding the chemical makeup of the entire universe. The periodic table's significance extends far beyond academic chemistry. Its elegant structure has led to discoveries and innovations that have transformed our world in ways Mendeleev could never have imagined. Consider semiconductor technology, the foundation of every computer, smartphone, and digital device you use. The entire electronics revolution is built on understanding how elements in the same group of the periodic table share similar properties. Silicon and germanium, both in group 14, have the perfect electron configuration to act as semiconductors. By adding tiny amounts of elements from neighbouring groups, a process called doping, engineers can control exactly how electricity flows through these materials. The development of modern materials science relies heavily on periodic trends. Engineers use the table to predict how different elements will behave when combined, leading to everything from super strong alloys used in jet engines to the rare earth metals that make possible the powerful magnets in wind turbines and electric car motors. Medical isotopes represent another unexpected application. Many elements have radioactive versions that decay at predictable rates, making them perfect for medical imaging and cancer treatment. Technetium-99m, derived from an element that doesn't naturally exist on Earth, is used in millions of medical scans each year because of its nuclear properties, predicted by its position on the periodic table, making it ideal for imaging internal organs. Even the development of new pharmaceutical drugs relies on the periodic table principles. Medicinal chemists use their understanding of how different elements behave to design molecules that will interact with the body in specific ways. The difference between a life-saving medicine and a deadly poison often comes down to substituting one element for another based on their periodic relationships. This iconic chart remains far more than just a list of elements. It's still a powerful predictive tool that drives modern scientific discovery. Scientists today use the same principles that guided Mendeleev to anticipate the properties of materials that haven't yet been created, to design new catalysts for chemical reactions, and to understand complex biological processes. The table provides invaluable insights into understanding chemical behaviour at every level, from predicting how elements will react to form compounds, to understanding their physical properties like melting points and electrical conductivity. The periodic table remains a fundamental guide for anyone working with matter at the atomic level. It continues to serve as an educational cornerstone. The elegant structure makes complex chemical concepts accessible, revealing the underlying patterns that govern how atoms interact. Students around the world still memorize portions of the table, not just as an exercise in rote learning, but because understanding these patterns provides intuition in how the natural world works. Ultimately, the periodic table stands as a symbol of scientific progress and human ingenuity. It represents humanity's ongoing quest to understand the universe and its fundamental constituents. In an age where scientific knowledge can seem fragmented and specialised, the periodic table reminds us that underneath the apparent complexity lies elegant, discoverable order. The table embodies the best of the scientific method: careful observation, pattern recognition, bold prediction, and experimental verification. It shows how individual discoveries by different people in different countries and different eras can build upon each other to create something greater than the sum of its parts. Perhaps most importantly, it demonstrates that the universe is knowable. In a cosmos that can seem random and chaotic, the periodic table reveals that matter itself follows discoverable laws. The same patterns that govern the behaviour of elements in a chemistry lab on Earth also determine the composition of distant stars and the formation of planets. And that brings us to the end of our journey through the history of the periodic table. We've explored the early attempts at organisations by pioneers like Döbereiner, Chancourtois and Newlands. We've delved into the monumental contributions of Dmitri Mendeleev, the tragic brilliance of Henry Moseley. We've examined the human dramas and rivalries that shaped scientific progress, followed the modern quest to create new superheavy elements, and contemplated the cosmic origins of the elements themselves. The periodic table is far more than a chart hanging on classroom walls. It's a testament to human curiosity and ingenuity, a beautiful and complex system that reveals the underlying order of the universe. It's a tool that's driven countless discoveries and continues to guide scientists in their quests to understand the fundamental building blocks of matter. From predicting the properties of undiscovered elements to understanding the nuclear processes that power stars, the periodic table remains one of science's greatest achievements. And most remarkably, is it still growing. As scientists push the boundaries of what's possible in their laboratories, creating elements that exist for mere moments before decay, they're continuing the same tradition of discovery and organisation that began over 150 years ago. Each new element added to the table is both an end and a beginning, the culmination of years of painstaking work and the opening of new questions about the nature of matter itself. Next time, though, we are switching gears completely. We'll be rolling for initiative as we dive into the world of fantasy and adventure, where we explore Dungeons and Dragons. We'll be having a look at its history, its impact on culture, and why this tabletop game has captivated millions for decades. So thank you for joining me today on this journey through the elements and the brilliant minds who organised them. As always, I've been your host, Jack, but until next time, keep questioning and exploring.